Okay, welcome to the second video. This is today you're going to learn how electrons are arranged around a nucleus. Um, when we talk about electrons around a nucleus, we often draw it this way. This model is called the Bohr model, and we put the electrons into these circles. Now, it's important to realize that this is a model. There are better models. The better models don't really describe them as being in such discrete um, orbits. In fact, there are suborbitals, and there are different energy levels, as you can see, within these different suborbitals, and so more of like an energy cloud rather than these distinct orbitals. But this is how I want you to imagine it using the current Bohr model. Now, what does it mean for an electron to be at this inner circle as opposed to the middle one, as opposed to the outer one? Well, I want you to imagine them as energy levels, and you can think of it like this. Imagine we had a spike into the ground, and a like an elastic band tying you to that spike. If you were feeling a bit lazy as you were running around this spike, you would imagine that you wouldn't stretch that elastic band very much. If you drank an energy drink and did whatever else and got a bit more energy, you would be able to pull away from that center spike a bit more, wouldn't you? As you had more energy, you would move further away, and the elastic band would stretch further and further. And if you got more and more energy, you'd be moving further and further away. Well, there's two things happening there that kind of relates to that. So they have a higher energy, which allows them to pull further away from the nucleus, but there are also some electron shielding going on, which means that these electrons in here, they're negative, and negative repels a negative. So if you have too many negatives kind of hanging around this in a bit, it's going to start pushing one further out. So there's simply not enough room to hold it in. And then you're going to be able to fill out here, and then it's going to be able to push out another one. That's what's going on with those. So as I was saying, the more sophisticated model kind of talks more about an electron cloud, but for the moment, let's talk about orbits. When you're drawing your Bohr model, it's important to fill out the inside one first, and you need to know that on the first shell, there's only 2 available electrons. In the next shell, there's 8. And they start filling their way out. So what rules do we use? We use this rule called the 2n squared. So where n is the shell number. So if n is 1, 2 times 1 is 2. 2 times 1 is 1. Right? 1 squared is 1 times 2 is 2. Ugh, wow, that was embarrassing. Now that's recorded. Anyway, n is 2. 2n squared is 8. When n is 3, 2n squared is 18. Where n is 4, 2n squared is 32. Okay. The only other rule that's important to know is that the outer shell can't hold more than 8 electrons, and we're going to see this number 8 coming up again and again, and that'll make more sense to you as you kind of go through. But this is the rule that you'll use to draw your Bohr models. Let's have a look at this in practice. So if we have a hydrogen, we can just put 1 in straight away. Okay, we have a helium, we can put 2 in. All right, lithium, we can put 2 in, but the first shell can only hold 2 overall, can't it? So then the third one has to go into the second shell. The carbon, the inner shell can only hold 2, and then the other 4 have to go in the next shell up here. Fluorine, 2 in here, and then 2, 4, 6, 8 over here. Neon has 2 here, and then 2, 4, 6, 8. All right, 8's the maximum that it can hold. We move down to sodium, 2 in here, 2, 4, 6, 8, and 1 has to be pushed up, because 8 is the maximum that the second shell can hold. Moving on to silicon, chlorine, and argon. Now you notice the way it's been drawn here is the way I want you to draw it as well. When you're drawing them, you can draw them as X's or circles, it's up to you, but I'd like you to do north, south, east, west. North, south, east, west, and I want you to pair them up. Please don't draw 1, 2, 3, 4, 5, 6. You know, they don't appear that way. They actually appear in pairs, and it's nice to space them out. So north, south, east, west. Okay, so when we talk about um, figuring that out for the first 20 elements, right, has one atomic number, which means one proton, which means that if we're talking about an atom, right, means that there'll be one electron, and that one electron will go in the first shell. Looking at chlorine, okay, um, it's got 17 protons, 17 electrons. So we have 2 in the first shell, 8 in the second shell. Nice. After the first 2 are full, we know that's 10. 2 plus 8 is 10. Then 7 is going to go in the third shell. By the time we work down to something like calcium, we have 2 in the first shell, 8 in the second shell. Good. So we've got our 10. We've only got 10 more to do. And then we've got 8 here and 2 here. Now the question has to be, why is the third shell only have 8 and not 10? After all, 2 times 3 squared is more than 8, right? Let's not, trick me with the mathematics like you did before. So the answer is because the outer shell cannot have more than 8. Right? So if this had 10, then the outer shell would have 10, wouldn't it? The outer shell cannot have more than 8 electrons. So over here is now the outer shell, which is now the fourth shell, has 2 electrons. So this kind of activity is really common. We would ask you to draw the Bohr model and then write the electronic configuration as below. Now I want to move on really quickly to excited state and ground state, something that's to do with the energy levels of electrons. Before we were talking about how as um, an electron gets more energy, it moves to an outer shell, and this is exactly what's happening here. So if you put a metal ion into some flame or set it on fire, those electrons will become excited. The electron from here will actually move to here and go to a higher energy state. That electron will then eventually cool, and as it cools, it'll move back down to its ground state, and that energy was released as light, as a photon. Right? Don't worry about the mathematics, but as you put energy in, the electron goes from ground state to excited state, and then as it goes from excited state to ground state, it has to release that energy as a photon. You can see the same thing happening here with these the distances between the electrons between the shells results in the wavelength of light being produced. So hydrogen is going to produce these wavelengths, helium produces these wavelengths, and neon produces these wavelengths when set on fire. A short note about noble gases. We're talking about 8 being special. You'll notice that if you imagine this is the first shell, this is the second shell, this is the third shell, because remember that each period represents one additional shell, right? So in the first shell, you'll notice that there are only 2 elements here, aren't there? Right? So this helium has a full outer shell, right? The second period, this element here has a full outer shell, and it also has 1, 2, 3, 4, 5, 6, 7, 8, doesn't it? Right? Here we have a full outer shell, and it also has 8. So this, what's called the octet, like octagon is an 8, octet rule means that it wants to get to this full stable outer shell, and these noble gases are well known to be very stable. And that's all we're learning today. But next video, we'll look at the trends. Thanks.